So now that we're feeling pretty comfortable with trig functions, let's start talking about inverse trig functions. That's going to allow us to solve a lot of application problems, being able to compute inverse trig functions. So our learning objectives for the next little while are to determine exact values of inverse trig functions at special angles, because you don't get your calculator for test 2. Determine exact values of composition of trig and inverse trig, which isn't always as straightforward as it looks, and work on some application problems, which sometimes you'll need your calculator to solve. Those won't be on your test. If they're on your test, special angles. So you're going to learn that unit circle really well. So here's just kind of an overview of trig versus inverse trig. So trig functions have a domain or inputs that are angle measures. So their domain is either radians or degrees. Their output is a ratio or a number. Inverse trig are the opposite, because that's how inverse functions work. So the domain is a ratio or a number, and the output, and I'll use the fancy math word this time, the range is radians or degrees, angle measure. And of course I'll change that in a minute. So sine of y is equal to x, then inverse sine of y is equal to x, or arc sine. So is equal to arc sine of x does not equal sine of x to the minus 1 power. This is cosecant. So if the -1 is sitting right here next to the sine, that means inverse sine, not 1 over sine, which is cosecant. So if sine is pi over 6, then inverse equals 1/2, then inverse sine of 1/2 is pi over 6. Cosine of pi is equal to -1, so the inverse cosine of -1 is equal to pi. Tangent of pi over 4 is 1, so inverse tangent of 1 is pi over 4. Now, hopefully you took a few minutes to review inverse functions. Only one-to-one functions have inverses that are functions, and we really want inverse sine to be functions, so we have to limit the domain. We limit the domain so that the trig functions are one-to-one. Remember, to be a function, you have to pass that vertical line test. If every vertical line only hits that function once. To be a one-to-one function, you have to pass that horizontal line test, because remember, they switch roles. So what became the horizontal line test for the function is the vertical line test for the inverse function, so it has to pass both in order for it to be a function. So I'm going to bring up some graphs. Let me pause. So this is a graph of sine, and you can see it absolutely does not pass that horizontal line test. So we have to take just a piece of it, and we have all decided that the piece that we are going to take is the interval from -pi over 2 to pi over 2. So that right-hand side of the unit circle. We do the same thing for tangent. Here's tangent. Let me turn off sine. We look at just that piece from negative pi over 2 to pi over 2. Cosine's a little different. If we looked at the piece from negative pi over 2 to pi over 2, that would not pass the horizontal line test. So instead, we look at that top half of the unit circle from 0 to pi, and we have a little piece of cosine that passes the horizontal line test. So, for sine, we restrict the domain to negative pi over 2 to pi over 2. Again, if you're looking at your unit circle, it's the right-hand side of the unit circle, negative pi over 2 to pi over 2. So if the domain of sine is negative pi over 2 to pi over 2, and we know the range of sine is negative 1 to 1, that means the domain of inverse or arc sine is negative 1 to 1, and the range is negative pi halves to pi halves. Similarly, let's look at, there's the inverse sine function. Let's look at cosine. So cosine, we restrict the domain 0 to pi. So cosine, we go from 0 to pi for our domain. Our range is negative 1 to 1. So for inverse or arc cosine, our domain is negative 1 to 1, and our range is 0 to pi. There's the pretty picture. And you notice they are reflected about the identity line, just like all inverse functions are. Tangent's a little different because tangent, the domain is restricted to the open interval, not the closed interval, because tangent doesn't exist at pi over 2 because it's sine over cosine, and cosine is equal to 0 at pi over 2. So we're going from negative pi halves to pi halves, and the range is all real numbers. So arctan, or inverse tan, the domain is all real numbers, and the range is negative pi halves to pi halves. There's the pretty picture. So let's do some evaluating. We want the inverse sine of 1/2. And I always think about the unit circle. So I'm going to draw myself a little unit circle. For inverse sine, I'm looking for an answer over here on the right-hand side of the unit circle. This is a positive number, so I know it's going to be above the axis. And sine is 1/2, so I know that it has 6 in the denominator. So pi over 6, and I have to work hard to remember the degrees. That would be 30 degrees. I'm really good with the radians. I have to work at the degrees. B, we have arc sine. So same function, just a different way of referring to it. Negative square root of 2 over 2. So I'm still on the right-hand side of the unit circle. This time it's negative, so I know it lives below the x-axis. and it's square root of 2 over 2, so I know that it has 4 in the denominator, so it's negative pi over 4, or negative 45 degrees. Inverse cosine, or arc cosine, of negative square root of 3 over 2. So this time, I'm looking at the top half of the unit circle. Cosine's positive over here and negative over here. So I know my answer lives on this part of the unit circle. And since it has pi square root of 3 over 2, I know that it has 6 in the denominator, because I know that the little triangle would be wider than it is tall. So it is 5 pi over 6. And now this one would be 180 minus 30, which is 150 degrees. And finally, arctan of 1. I always think of that as that's when sine and cosine are the same. So it has 4 in the denominator. We're back to the right-hand side of the unit circle. So pi over 4, because tangent's positive up here. And here are all our pretty answers. So, your turn. Give these a try. We'll meet back and compare answers in a moment. How did it go? So, inverse sine of 1 is equal to pi over 2, because sine of pi over 2 is equal to 1. And pi over 2 lives in that restricted domain, so it's in the range of inverse sine. Even though sine of, if we add another loop around the unit circle, so sine of 5 pi over 2 is also equal to 1, that's not the correct answer. Similarly, inverse tangent of square root of 3 is equal to pi over 3. That lives in quadrant number 1. Tangent of inverse tangent of square root of 3, well, excuse me, tangent of, let's see, 5 pi over 3. No, 7 pi over 3. 7 pi over 3 would be in quadrant number 3. So tangent of 7 pi over 3 is also equal to square root of 3, but that's not the correct answer because it's not in the range of arctan. Arc cosine, well, we just saw that when we were confirming that inverse tangent of square root of 3 is pi over 3, because sine of pi over 3 over cosine of pi over 3 is square root of 3 over 2 divided by a half. Cosine of pi over 3 is 1/2. Okay. Evaluating compositions. So here's just a little summary. If you take the sine of inverse sine and x is between -1 and 1, it's easy. These are all the easy conditions. If your x's are not within those restricted domains, then you have to work a little harder. Let's look at an example. I have the inverse sine of the sine of pi over 3. Now, if we look back at our little summary here, inverse sine of pi over 3, well, pi over 3 lives right in that range, the restricted domain for sine. So this one is just pi over 3. If we look at the sine of the inverse sine of 1/2, My answer is just 1/2 because that lives in that interval between -1 and 1. Now let's look at the inverse tangent of the tangent of -225 degrees. Now, we've talked about what our restricted domain is in terms of radians, but not degrees. So if we're looking at this right-hand side of the unit circle, this is 90 degrees. This is -90 degrees. Well, -225 does not live in that little area there. So we're going to have to figure out what the tangent of -225 degrees is. So, inverse tangent. So let's see. This would be -90. This would be -180. So this would be 45 degrees more. So we would be right over here in quadrant number 2. So tangent of -225 would be -1. And the inverse tangent of -1 lives down here where sine is equal to negative square root of 2 over 2, and cosine is positive square root of 2 over 2. So this would be negative. And since the question was in degrees, we'll give the answer in degrees. Let's look at the inverse sine of the cosine of 13 pi over 6. So 13 pi over 6 certainly is not within our restricted domain. Cosine of 13 pi over 6, well, that's all the way around the unit circle and back up to pi over 6 again. So this is the inverse sine of the square root of 3 over 2. And the inverse sine of the square root of 3 over 2, well, that's going to have 3 in the denominator, and since it's positive, it lives in quadrant 1. Cosine of arc sine of 7 over 9. So if arc sine of 7 over 9 is equal to theta, then sine of theta is equal to 7 over 9. If sine of theta is equal to 7 over 9, then sine squared of theta plus cosine squared of theta is equal to 7 over 9 squared plus cosine squared of theta has to be equal to 1. So 49 over 81 plus cosine squared of theta is equal to 1. Cosine squared of theta is equal to, I'm going to do this with a calculator, 81 minus 49 equals 32. So 32 over 81. So cosine of theta is equal to the square root of 32 over 81. And let's see, this is 16 times 2. So 4 times the square root of 2 over 9. So this is 4 times the square root of 2 over 9. So it doesn't always have to be a special angle if we're doing a composite. So give these practice problems a try. Remember, first thing you ask yourself is this input within that restricted domain? If it is, easy. So give them a try and we'll meet back and compare. So part A was easy because pi over 9 lives over here on the right hand side of the unit circle. So inverse tan of pi over 9 is just pi over 9. Inverse cosine of 13 pi over 6. Well, 13 pi over 6 doesn't live in there, and we have sines and cosines, so I just compute cosine of 13 pi over 6, which is the same thing as cosine of pi over 6, which lives here in quadrant 1. Cosine of pi over 6 is square root of 3 over 2. Inverse sine of square root of 3 over 2 is pi over 3. Similarly, we have to compute the sine of negative 11 pi over 4, which is the same thing as the sine of negative 3 pi over 4. I just added 8 pi over 4, 2 pi to it. And then sine of negative 3 pi over 4 lives there in quadrant number 3, so it's negative square root of 2 over 2, and inverse cosine of negative square root of 2 over 2 is 3 pi over 4. Now these next practice problems are a little different because they require you to use your Pythagorean theorem. So give those a try, and we'll meet back and compare answers for these. So how did they go? Let me get it back on the right page because I went and checked. Yeah, I did have the exact same problem for D as I had for E in this one. Cosine of arc sine, cosine of inverse sine. So you probably noticed that as you started working on it. But we'll start with the part A. We had sine of inverse cosine of 4 over 5. So we just did the Pythagorean theorem. And then we thought about the fact that if sine squared is equal to 1 minus 16 over 25, then sine is equal to plus or minus, and we had to think about what quadrant we were in, which we kind of glossed over during that first example. So now we'll go back and talk about that. Since cosine is positive, that means we're in quadrant 1, is the inverse cosine. We're taking the inverse cosine of something positive. That means that theta is in quadrant 1, so that means sine is also positive. So sine is 3/5. If we have cosine of inverse tangent, again, if tangent is positive, if we're taking the inverse tangent of something positive, that means our answer is going to be in quadrant 1, so cosine will also be positive. And I just drew a triangle and did SOHCAHTOA. So tangent of theta is equal to 5 over 12. And then hypotenuse is 13. I did the Pythagorean theorem. And cosine is adjacent over hypotenuse. Similarly, for sine and tangent, going to have the same signs when you're doing the inverse tangent of something sine because they both are on the right hand side of the unit circle. So I did the triangle again. This one wasn't as pretty. It had a square root of 65 in it. So sine is opposite over hypotenuse. And then the last one, again, since we're doing inverse sine of 7 over 9, that means theta lives in quadrant number 1, and so cosine is equal to 4 times the square root of 2, over 9. Alrighty, so we can use inverse trig functions to determine angle measures given a right triangle with 2 known side lengths. SOHCAHTOA. So sine is equal to opposite over adjacent, and cosine of theta is adjacent over hypotenuse, so theta would be the arc sine of adjacent over hypotenuse, just like we've been doing. So let's do a no calculator example. Determine the exact value of theta in degrees. And of course I have to redraw the picture myself because it helps me to understand what's going on. example 3, theta is living right here in this corner. Here's my right angle. And I have op is equal to 6, and hypotenuse is equal to 12. So that means sine of theta is equal to 6 over 12, which is 1/2. So theta is equal to pi over 6, or 30 degrees. There's the pretty answer. Now, in the real world, not all angles are special. You might need a calculator. So determine theta in degrees to 1 decimal place. So example 4. Again, I have my right triangle. I'll put theta right here. Adjacent is equal to 4, and op is equal to 3. So really this one you could do without your calculator, because this has to be a 3, 4, 5 triangle. But we'll go ahead and figure it out. So we have the tangent of theta is equal to 3 over 4. No, I'm wrong. We could easily figure out what the hypotenuse is, but we want the inverse tangent of 3/4 in degrees. So I'll get my degree calculator, turn it on, and do inverse tangent of 3 over 4. Yeah, it's not obvious. It's 36.86, and we wanted 1 decimal place, so 36.9 degrees. And there's the pretty answer. And here's the practice problem. So determine the value of theta in degrees and in radians. So this one we had adjacent and hypotenuse, so we use inverse cosine of 9 over 12. Now I just plugged it into first my calculator that's in degree mode, and then I plugged it into my calculator that's in radian mode. You could do it in either one and just convert, because you know how to do that. You did it on test 1. So you have all the knowledge that you need to go forth and complete your assignment on inverse trig. You can do it.